Thanks for introduction. Thanks for us to come to this session. In this session, we will talk about how to use Spark and machine learning, especially the ML lab, to using in online e-commerce and retailer industry areas. I will take Jingdong with the example, and Ruifeng comes from Jingdong. He's a senior software engineer at the intelligence advertisement lab of Jingdong. Jingdong has a lot of data and a lot of business scenarios. And he contributes a lot of software like Spark, Scalon, and SD Boost. And my name is Yanbo. I'm a staff software engineer at Hortonworks, and also an Apache Spark PMC member. I also contribute like TensorFlow and SD Boost. So in this talk, you will get first, Ruifeng will introduce about the business scenarios, the problems they face at Jingdong, because Jingdong has a lot of users and will produce a lot of data, and also has a very interesting questions we want to solve and how they solve it. And then I will introduce about the lesson we learned during we work together to give the deliver the better solutions for the customers, and we want to introduce the improvements in the Apache Spark community to help them. And still, there is some gaps between the currently Spark and their requirements. So at last, Ruifeng will introduce about the enhancements they did for ARS and Spark GBM. So okay, let's give Ruifeng for the introduction.
Thank you. First, let me introduce something about Jingdong. Jingdong is the largest online retail in China, which has the largest e-commerce delivery system. Over 90% of orders are delivered the same or next day. There are more than 300 million of active users with billions of SKUs. And I needed the data mining team named Ruifeng in business growth department at Jingdong. Our duty is to supply data mining service for top brands. Since we directly solve for the top brands, we have encountered various business problems. Among them, several common scenarios can be summarized. They are user segmentation, cross-selling, and purchase prediction. First, let me introduce something about user segmentation. Current advertising system usually supply purchase-based metrics like ROI or GMV to measure the marketing campaigns. However, brands need more meaningful information. To address this problem, we need to use various data sources. We include the impression log, click log, search log, and other kinds of data sources. And then we need to design a segmentation model to take them all into account. We first studied the marketing model proposed by Philip Keller, who is known as the father of modern marketing. Then we take our data situation into account and design a marketing model named 4A. Our model segments users into 4 categories. The first is aware, which means initial touch, like AD impression or view. The second A, appear, means more views, search, add to cart, follow, and ask. The third A, act, is just purchase. The last A, advocate, means high rating or positive comments. With the 4A model, we obtain status of each user. In practice, we first apply RDD to implement the model. When data frame is stable enough, we transfer to it, and RDD is still used in some complex operations. The refactored one is about 3.2 faster than the old one and save about 40% memory footprint. The second theory is about cross-selling, where is originally the action of selling additional products. This picture shows a famous story. Beer and nappies. The story says that fathers are going to buy nappies for their babies, and since they can no longer go down to the pub as often, they would buy beer as well. As a result of this finding, the supermarket set the lapis next to the beer, resulting in increased sales of both. There are millions of brands in Jingdong, and it is very natural that our customers ask this question: which brands are best cooperates for the cross-selling? Suppose we serve brand Y and we are asked to give a list of potential brand X. We use the frequent pattern mining in MLlib to mine the potential cooperates. It will select the frequent item set by matrix support, which means fraction of transaction that contains both X and Y. MLlib implements FP growth for this purpose. Then the candidates of those like brand X to brand Y are generated and they are measured by matrix confidence, which means the expected probability that brand Y would occur when brand X occurs. MLlib implements prefix span for this purpose. Use the above two functions, we can list potential brand X with high support and high confidence. However, we should keep in mind that high confidence doesn't always mean brand X has potential influence. We have encountered a special case that the confidence is about 5%, which is a relatively high value, but the proportion of purchase of brand Y in all users is about 6%. This means that brand X has a negative influence on brand Y. Also, the confidence is a high value. To make sure that brand X can improve sales of brand Y, we should use an additional matrix lift. It measures how many more times X and Y occurs together than expected. And by the way, MLlib's implementation only supports mining rulers which has a single item as the consequent. However, in some special case, our customer asks us to mine more complex patterns like sets A, B, C to set X, Y. To address this, we have developed a new implementation, and it can be found in this corresponding ticket. The last theory is about helping brands to better target potential purchase. We mine millions of users and upload them to our advertising system. Then brands can direct target them. In the data flow, we first built a recall model, which is composed of rulers and machine learning models like ALS. We then applying a ranking model. We assign the past purchase as the positive samples, and those who have touched our target items yet not buy it are the negative ones. Then we use binary classification to model the point-wise ranking. After the model is established, we select a user with a high score and upload them into the advertising system. This slide shows our ranking structure. We use Spark Circle to extract features from users, items, and context. We then train classification models on distributed systems. Some models are trained on Spark, which are yellow field. Others are trained on deep learning framework like TensorFlow or MXNet. And then we use Spark ML's algorithms like logistic regression and random forest. We also use some in-house implementations like gradient boosting machine and factorization machine. Then we introduce our modeling pipeline and how Spark is used in it. We use a standard methodology named CRISPR-DM. Its full name is Cross-Industry Standard Process for Data Mining, and it is one of the most widely used forms of data mining models. It breaks the process of data mining into 6 major steps. We first communicate with our customer to discuss the demands and do rapid data exploration with the Spark shell to verify the ideas. If the result seems fine, we then go to data preparation with the Spark SQL. Then we train models and evaluate them with MLlib, and maybe go back to the preparation if necessary. If the model works well offline, we will deploy it on Spark streaming and monitor the online metrics. Then Yanbo will summarize the lessons we learned in practice, our contribution to the community, and what we benefit from others' communications.
Okay, thanks, Ruifeng. Just like Ruifeng mentioned, the pipeline is a good thing, and many users will benefit from the design of Spark pipeline, especially the machine learning pipelines. And Ruifeng mentioned that at Jingdong they use several algorithms like the LLS, like logistic regression, like the frequent patterning mining. So the feature preprocessing is also a very important step before using the machine learning algorithms. MLlab provides many transformers you can use to transform one kind of data frame to another ones for data processing. But for a long time, MLlab only support apply feature transformers on one columns each time. It means if you want to transform maybe 10 columns, you need to do it one by one in serialized mode. So this may be time-consuming and waste several resources. So recently we worked together like Jingdong and other community members to did optimization for the feature pre-processing steps. Almost all the feature transformers in MLlab currently supported running multi-columns transformer at the same time. This can save a lot of time. You can see from the diagram. We can get a great improvement. If you want to transform like 100 columns, you can get almost 10 times accelerations. And almost all the transformers currently supported transform parallel. And another lesson we learned is, as we all know, data frame currently is the de facto API of Spark, but we still use like RDD API. In general, we are recommended to use Spark data frame or dataset API because it can help us to save some memories, help us to do circuit query optimizations. It can benefit a lot of use cases like ETL, like data analysis. But for machine learning, the case may be different. Because for machine learning, if we want data frame or dataset API, we need to do a lot of serialize and deserialize. There are a lot of cost. So for machine learning, we may use a data frame API called dataframe.rdd. And we first convert it from data frame to RDD, and then to execute some operations on top of RDD. And actually, almost all those algorithms currently implemented in Spark MLlab are using the same way. So if you use your own algorithm, if you implement your own algorithms, you can consider follow the same way. And another great benefit is like the picture showed. If you attend the talk yesterday by Brent and Nick, they have given the detail of the parallel cross-validation. But we are not the developer of this feature, but we are maybe the best benefit of this feature, because before the Spark 2.3, if you submit multiple Spark jobs, for example, if you run a four-fold cross-validation, there will be 4 jobs to run simultaneously. But before 2.3, the job is submitted one by one. You can think it will take a lot of time to finish the job, even you have enough resource. But after 2003, we have a new API for cross-validator called set parallelisms. You can set maybe 5 or 4 to the parallelism. Then you can submit 5 jobs at the same time, and the job will run parallel in your cluster. If you have enough resource. So Ruifeng has did the performance at his clusters because they have a very large cluster, has thousands machines and running Spark on Yarn. And they can find that this cross-validations can get a great improvement, great speed up for the scenarios. So they also, these features also make their work very, very efficient. But we have introduced the benefit we get during the Spark 2.3 release and some of the work that contributed by the community. But there are still some gaps that are required by a lot of companies like Jingdong or other companies. And the first one is like warm start, because for example, if you're training like a logic regression, you will not run from scratch, train from scratch each time. Maybe next time you have new data, and you may be train the model from a checkpoint. So like continual training, and it can get maybe a more stable solution, and it can accelerate the conversion speed. And another big requirement is some callback mechanisms after each iteration. For example, if you have an evaluation data set, if you evaluate your model on the data set, you can say, oh, the model is good enough, then we can early stop. We won't wait the number we set, we stop. So its early stop is maybe a mechanism to help you get to train your model more fast, and some model checkpoint, because you train several iterations, you want to checkpoint at some time and recover at the checkpoint. This is same as this is also benefit for the warm start. So and there are some other issues like the numerical format support. So for these kinds of requirements, the currently Spark didn't have did some work until now, but maybe in the future we have some some improve. But Ruifeng and Jingdong has, as Ruifeng's team, has did some improve for the ARS and GBM, and they has also benefit this improvement. It can help them to get more accurate model and make their model run fast. Like Ruifeng gave the introduction of the detail.
The first enhancement is to support warm start and model checkpoint in ALS. MLlib implements ALS for recommendation. It decomposes the user item ranking matrix into latent factors of users and items, and the latent factors can be used to predict missing entries. The ALS tries to find the optimal factors to minimize the error between prediction and actual ratings. In our case, it takes several hours to converge. Since our team uses Spark on a large public cluster with thousands of nodes, the training may fail due to some other side influence. We save the model snapshot after each iteration. When the training fails, we can continue the training progress just by loading the last snapshots. In the training, we adopt warm start to accelerate convergence. We updated the ALS model day by day, and we design a warm start method to speed up training. Suppose there are 3 items, A, B, and C, at time t, and we train a model. In the next time before training, we first load the previous model. If some items are no longer available, such as the item C, just discard the corresponding factors. If some new items appear, such as item D, we use random vectors as the initial factors. After this initialization, just optimize the factors like the previous version. We also try to initialize the new item factors with the average value of the corresponding category. However, this makes no difference. We test warm start on a dataset of 50 billion non-zero ratings. We use 500 cores and 10 terabytes memory. Experiments show that with warm start experiments show that with warm start ALS take less iterations to convergence. The orange yellow ALS will take 6 more iterations to converge to the same loss, and the warm start saves about 40% training time. Another enhancement is to implement a modern gradient boosting machine. I think it is safe to say that GBM is a core algorithm. It is widely used in Windows solutions in the online contexts like Kaggle. It trains base model one by one, and the objective in iteration T is composed of regulation and the training loss. And the GBM aims to obtain a potential value to be added to the previous base models. There are many implements of GBM. First, GBT is proposed. It chooses descending tree as the base model and uses first-order approximation of loss function. The XGBoost introduced second-order approximation, regularization, column sampling, and other features than in light GBM. Discrete bins is used for performance optimization, and histogram subtraction is proposed to have the communication cost. Compared to XGBoost and light GBM, Spark GPT has some room for improvement in terms of scalability, accuracy, and functionality. All of them have distributed versions. MLlib's GPT is atop Spark, XGBoost atop Rabbit, and Light GBM atop DMTK. However, dedicated ML frameworks like Rabbit and DMTK result in extra costs in deployment, maintenance, and resource monitoring. So we implemented a new GBM atop Spark, Spark GBM. It absorbs major features from CounterOnes and adopts Spark as the computing framework. Spark GBM supports both data frame-based API and RDD-based API. It is totally compatible with the MLlib pipeline. It supports warm start and early stop. And the RDD-based API also supports user-defined functions like objection, evaluation, and callback. Here shows the data frame-based API. The estimates GBM regressor and the GBM classifier support various boosting type, objectives, regularization, early stop, and warm start. And it also supports training with validations, feature transformation by index of paths. We test all the implements on a dataset of about 110 million samples. We use 1,000 cores and 10 terabytes memory. We can see that our Spark GBM is about 2 to 3 times faster than current GPT. However, it is still twice slower than XGBoost 4G. We digged into the case and found that one important reason lies in the model updating scheme. Rabbit use or reduce to update the models, which is more efficient than the reduce and broadcast style in Spark. In the future, we will go on some enhancement of MLlib. We will try to apply warm start in other algorithms. For example, we found that GMM cannot converge well in some cases, and sklearn use k-means for initialization to overcome this. We will try to study this case on Spark. Then, current warm start of AS do not make a solution stable enough. We will try to resolve it. And we will add more features from XGBoost and Light GBM to enhance our Spark GBM. That's all. Thank you.